Welcome to The Explainer. Today, we're diving into the invisible chemistry that's happening all around us, like right now. We're going to break down the basic rules that govern everything, from a simple melting ice cube to a rusty old nail.
All right, so here's what we've got on tap. First, we'll look at the changes happening everywhere. Then, we'll get into the recipe for chemical reactions and figure out chemistry's great balancing act. After that, we'll check out a whole catalog of reaction types and, finally, see how this stuff actually shows up in our day-to-day lives.
Okay, first up, changes all around us. So, our world is always in motion, right? But it turns out there's a massive difference between, say, an ice cube melting and a log burning in a fireplace. One you can reverse, the other, not so much. Let's dig into why that is.
So you've got two kinds of changes. First, there are physical changes. Think about water freezing into ice. Yeah, it looks different, feels different, but it's still just H2O. You can totally reverse it just by warming it up. But then you've got chemical changes, like milk going sour. You can't unsour milk, right? No way. That's because a totally new substance has been created. The change is permanent.
Right, so that permanent change, that's what we call a chemical reaction. And honestly, the best way to wrap your head around it is to think of it like a recipe. You've got your ingredients, and you combine them to make a final dish that's something completely new.
And here's the key takeaway. A chemical reaction is all about transformation. You start with some stuff, they get together and do their thing, and what you end up with is something entirely new, with its own unique properties. So, in our chemical recipe, the ingredients have a proper name. We call them reactants. Super simple, they're just the starting materials, the things that are about to, well, react.
And what about the final dish, the new thing you've created? Well, that's called the product. It really is that straightforward. Reactants react, and you get products.
This is just a perfect example of the whole thing. You take two reactants, right? Hydrogen gas and oxygen gas. They react, and boom. You get a totally new product, liquid water. The original ingredients are just gone, and something new is in their place.
Okay, so next step is what I like to call the great balancing act. See, chemists write these reactions down as equations, but you can't just scribble whatever you want. There's one single, absolutely unbreakable rule of the universe that every single one has to follow.
So, did you ever wonder in science class why the teacher was so obsessed with balancing equations? I mean, what's the big deal? It's not just about keeping things neat and tidy, I promise. There's a really deep fundamental reason for it.
And here it is, the law of conservation of mass. This is a big one. It's a fundamental law of physics of the entire universe. And what it says is that you can't just create matter out of thin air, and you can't make it disappear into nothing. In a chemical reaction, you're not destroying atoms, you're just rearranging them into new patterns.
So when you balance an equation, what you're really doing is just a bit of chemical accounting. You're making sure the books are balanced. The number of atoms for each element you start with has to be the exact same number you finish with. It's simple, really. What goes in must come out.
And this slide? It's a perfect snapshot of what an unbalanced equation looks like. Just look at it. The books don't balance at all. For iron, you start with one atom, but somehow end up with three. And for oxygen, you start with one and magically get four. As it's written right here, this reaction is literally breaking a law of the universe.
Now, once you get these equations balanced, you start to notice something cool. Chemical reactions aren't just random chaos. They actually follow very predictable patterns, almost like different genres of stories, each with its own kind of plot.
So first up, you've got the combination reaction. You can think of this as the simple love story of chemistry. Two simple things. Let's call them A and B. Meet, and they combine to form one more complex thing, A, B. Simple as that. And then you have the exact opposite. The decomposition reaction. This is the breakup story. A single complex thing, AB, breaks down into two or more simpler parts. The story of AB is over, and now you just have the separate stories of A and B.
Then things get a little dramatic with the displacement reaction. This is the story where a more reactive, kind of stronger element, A, comes along and just bumps the less reactive element, B, right out of its partnership with C. So A and C get together, and poor B is left all on its own.
And finally, we get to a really crucial pair, oxidation and reduction. You should think of these two as the yin and yang of chemistry. They're opposites, but they almost always happen together. In the simplest terms, oxidation often means gaining oxygen, while reduction means losing it. Now, I know that sounds a bit abstract, but trust me, you see the results of this pair literally every single day.
Okay, so why should you care about any of this? These different genres of reactions? What's the point? Well, the point is, this stuff is happening all around you, right now. So let's bring it right back into your home and look at the real-world impact of just one of those types, oxidation.
You see the handiwork of oxidation all the time. It shows up as corrosion. You know, that gradual destruction of metals. We're talking about rust on a bike, silver that's turned black, or that greenish coating you see on old copper. And you've absolutely tasted it as rancidity. That's the chemical process that makes old chips or cooking oil get that awful, stale smell and taste.
Which brings us to a question I know you've asked yourself. You open a bag of your favorite chips, and it's like half empty. So what's the deal with all that air in the bag? Are they just trying to rip us off?
Well, here's the secret. It's not air at all. It's actually almost pure nitrogen gas. And there's a brilliant chemical reason for that. The nitrogen basically acts like a bodyguard for the chips. It shoves all the oxygen out of the way, preventing that oxidation reaction, rancidity, from happening. It's the nitrogen that's keeping your chips fresh and crispy.
And just think about that. A simple bag of chips shows how this invisible world of chemistry is constantly shaping everything around us. It really makes you wonder, doesn't it? Right now, as you're sitting here, your body is digesting food. The battery in your phone is working, all thanks to chemical reactions. So the question is, what other invisible reactions are shaping your world right this second?